All right, so before we do that lesson for today, we're looking at number 17 and 18 from the homework or from the classwork. Yesterday, I didn't get to this one, but this one's an important one, and we can talk about both these. So on the sheet that had Kevin Hart at the bottom going like this, it says don't just stare at the problem. You know what I'm talking about? Okay, so on that sheet, that's kind of your bailout sheet. When you're simplifying, and also when you get to proving trig identities, when you get to proving them, a lot of times you're not going to know really what to do. You might have some ideas of how to simplify and clean things up. But if you don't know, then go to that sheet for hints on what to do. And after doing enough of these, a lot of those hints will kind of set into your brain as natural things to do. Like people say, oh yeah, changing things to sines and cosines. It's not always a great idea. I mean, sometimes it will work for you, but it'll make the process a 10-step process as opposed to a 3-step process or a 2-step process. So knowing all of the things on the sheet can be helpful when you put them all together. And again, simplifying doesn't just mean PEMDAS when it comes to trig stuff. All right, so that's why I gave you that sheet. It's just an additional thing to do that will help you simplify. So when I look at this thing, it already is sines and cosines. It already is in the numerator. Right? I don't recognize that as a fundamental identity. So there's a lot of things going on here that I'm like, well, what do I do? It'd be easy to get stuck. But one of the things on the list is what? Rhymes with tractor. Factor, yeah. So I look at this and maybe I go, oh, well, maybe it's a difference of 2 squares. So again, I don't know. I'm just trying stuff just to see if maybe something will help me. So I go, all right, well, let's just give that a shot. A difference of 2 squares, I would split that thing up as a sine squared and a sine squared. And if you don't know that, remember that sine 4 of x really means sine of x to the 4th. It's just the way mathematicians write it. So it'd be like having an x to the 4th minus a y to the 4th. X squared, y squared, y squared. So I'm going to break the sine and the cosine up, plus, minus. Now I'm starting to see something more familiar. And this first one, what's that look like? That's a Pythagorean identity, right? Sine squared plus cosine squared is 1 when there's a plus in the middle. So if that's equal to 1, basically 1 times this, now I'm just dealing with that. Now hopefully, because in a normal world we would have a quiz today over all the fundamental identities and then all the alpha minus beta identities. Actually, we would not have had a quiz on dang, it's a fuzz in my mouth. This is actually kind of an identity. I don't know if you remember this from last year, but do you remember the cosine squared x minus the sine squared x? Again, you guys didn't memorize these probably because you had open notes stuff, but this is actually the cosine of 2x. It's the double angle cosine. And there are actually 3 of these, which you really need to start memorizing all of those identities. Okay? But that's a double angle cosine. So this, to make it look like this, what would I have to do? To make that part take out a negative? So if I factored a -1 out of this, that becomes a negative sine squared. I can put it at the end. That becomes a positive cosine squared. And now that looks like a double angle cosine identity with a -1 out front. But these are the things that I hopefully, and you hopefully, will start recognizing when you memorize your identities and you recognize that as a Pythagorean. Or you look at this and a red flag goes off with you and you go, oh yeah, that's a double angle cosine. But you have to get to the point where you have these memorized. You guys will all be back in class, your whole class, you and the other 7, on the 22nd. And your test is going to be on the 23rd. Now, I'm not going to give you quizzes before then. I think I'm going to actually, like tonight, I think I'm going to post the quiz and the solution to the quiz for what you would have had today had everybody been here. All right, so you'll get a feel. If you want to take that quiz and take it and write down all the identities and anything you miss, if you miss a negative sign, you'd get the whole thing counted off. If you forget to square something, you would get the whole thing counted off. That's how I would grade this identities quiz. And there's a good chance you're going to have an identities quiz on the 22nd, even though it's not on that assignment sheet. So you might want to make a note of that 22nd identities quiz, because I'm going to give you one on test day. On the test day, I'm going to hand you a 1-page sheet and say, hey, here's your identities quiz. And then you're going to take it. It's going to take you 5-6 minutes. You're going to hand it in, and then I'll give you the rest of the test. You have to know these. Now, you got a gift this year. If you go and look at your identities page, which is this right here, you know most of these on this first page. And I talked about this with the class yesterday. Hopefully you watched the video. But you should know these right here. These first 6 groupings are Pythagoreans. The cofunctions I mentioned last year, but we talked about them yesterday in the video. They're basically, they're related by sine, cosine, tangent, cotangent, secant, cosecant. And basically it just says, with those cofunctions, the trig function of 1 is the cofunction's complement. So whatever you have here, just take the complement of it here, and that's related with secant, cosecant, tangent, cotangent, sine, and cosine. And either way, it doesn't really matter. So if that was a 20, that would be a 70. If this is a 10, that's going to be an 80. Are you with me? And then Pythagorean identities, we just used that one, but there are also these other 2, and I talked about those in the video where they came from, but you just need to have these memorized. So when, and bottom line, usually you're going to see them, not the entire identity, but you're going to see 2 parts of it. So in your head, you got to go, hey, if I ever see a tangent squared and a 1, I got to know that I can make a substitution use the secant squared. Or if I ever see a secant squared and a 1, I'm betting maybe that I can replace it with the tangent squared, like if it was secant squared minus 1. Or maybe if I see a cotangent squared and a cosecant squared together, there's a good chance it might be equal to 1 or negative 1, based on these identities. And the more you do these, the more you'll start, it'll be like a red flag that goes up and you're like, oh yeah, I can make a substitution there. And then these, even and odd identities, we've talked about as well. But today we're going to get into the alpha minus beta identities, this set of 6. And we're going to work with these. But you can see down here on the double angle cosines, that's the one we just used. Double angle cosine. And there's 2 other ones as well. And honestly, the 2 other ones, they just come from me making a Pythagorean substitution in here. And again, right now, if it sounds like I'm speaking French, remember, the Pythagorean substitution, like, you know how sine squared theta plus cosine squared theta is 1? Well, I could replace that if I subtract sine squared from both sides. I can replace cosine squared with 1 minus sine squared. And if I replace that with 1 minus sine squared theta, what do I end up with? 1 minus what? 2 sine squared theta. And if I do the same thing and replace the sine squared with the 1 minus cosine squared, I end up with that. So a lot of these other pairs of identities or other options for the identity is just me manipulating the first one. And there are proofs to all these. And I literally did a study one year. I mean, it wasn't like an advanced study, but I used to prove all these identities. I'd take a couple extra days and just prove them all. And I used to do that all the time. And one year, we were kind of running short on time, so I didn't prove anything. I just showed them how to use them, and my test scores went up. I'm like, what? So I started doing that. And then this test, which normally was really brutal, when I didn't show them the why, they actually did better. I was like, go figure. Normally, that shouldn't be the case. Normally, the why helps. But I found that showing this doesn't do as much. Maybe because people are like, ugh, I don't want to know why, just show me how. But I put all the proofs in the book. So you can see them if you hunt around in here. I'll have pages of, hey, here's the proof, here's the proof, here's the proof. And if you don't, ask me and I'll print you up something. If there's one missing. Sometimes I mean to do it in class, but just in the interest of time. And I'm still working to try to get everything in this year. Because every time I had a test, we've been losing a day. And I think I can. I've got everything in Algebra 2, and I'm still working on this class to get it done before Christmas. And get caught up. But anyway, you've got to know these identities. You guys will have a little bit of a break this year because I'm eliminating the hardest part of this course, which is pure math team junk. And this is your junior year. It's the last year we have a math team class anyway. Pretty good chance of us not having a tournament. And even last year, it's rare that one of these shows up. But one of these problems, when they do show up, this makes it really, really easy. But this last 3 groupings of identities are by far the hardest ones to memorize. They're not hard to use, but they're really hard to memorize. I mean, for me even. Right now, I'd have to go back and study these. It's really difficult because it's so irregular. Really hard to find patterns that make sense in your head. But we're going to cut all this junk out. That's why when you look at your assignment sheet, you can see, like on the review sheet, it'll say omit certain problems. I'm cutting these things out. So that's going to make your test significantly easier. Because like half the people miss these on the test, or more. So that's going to make this test a little bit easier. But But for those identities that are above this, above the power reducing, I think I'm going to leave the triple angles in there, but I'll show you how you can find those even if you forget them, because I forget them every year, but I know how to prove them in my head. Yeah. Yeah, if you need to get it, go. I don't have a calendar on whatever. Do you know your time?
If they just said 8:15.
Yeah, go. Yeah, just go if you got to go. Hurry back. But anyway, those are our trig identities, but guys, start practicing them now. It'll be a little easier for you because you won't have to worry about all these dirty ones right here. But start memorizing them now so you can do well on this test. All right, and then make sure you understand what each of these means. We just talked about how factoring comes into play, and the next one, we're going to talk about how creating a monomial denominator is going to come into play. So if you look at that second question Jordan asked about, number 18 or 19, what was it? 18. So on this one, I look at it and I'm like, well, it's already sines and cosines. I don't know how to bring this up to the numerator because it's joined with a minus, so it's not like I can change the cosine to a secant because it's connected to that one with a negative and positive. That keeps me from swinging it up. So I really don't know what I can do. It's not an identity. It's not squared, so it's not a Pythagorean identity. Like I can't replace 1 minus cosine squared with the sine squared because it's not squared. So when you run out of issues, that's why I put this one later on because it doesn't happen as much. But you could create a monomial denominator here. Right now it's a binomial. You could create a monomial by multiplying by the conjugate. So look what happens if I just multiply by a 1 plus cosine y. So when I do that on the top and the bottom, I'm not even going to multiply it out on the top. Because watch what's going to happen. If this is a process, it's going to happen this way. So don't multiply it out. Just leave it like this. But do multiply out the bottom. So on the bottom, if I FOIL this out, the inner terms cancel, and I get 1 minus cosine squared y. Oh my gosh, what's 1 minus cosine squared y now? Yeah, now it is a Pythagorean, and now that can be replaced with a sine squared y. So I'm going to replace that, and now look what I have. And this is why I didn't multiply it together. So make a mental note. Don't multiply it together so that when you simplify it, stuff cancels. And now that this cancels, I've got it down to a nice, simple expression. Are you with me? And at this point, I don't know what else I can do to this. If I try to add these, I mean, I just can't. I don't have, it's kind of like having x's and y's. They're unlike terms. So after I go through all those rules, if there's nothing else I can do, I'm good. Y'all with me? And it happens to be in the numerator. It's all sines and cosines. Win, win, win. All right? But that's an example of just something to kind of add to your tool belt of things to do if you get stuck. But like I think I said in the video yesterday, every year, well, maybe not this year, but most years people walk up to my desk, man, this problem's impossible. And I'm like, yeah, it's a tough one, man. What have you tried? No, I've tried everything. And literally I go, what? Have you maybe tried changing it to sines and cosines? And literally I'm reading off the list that's in my head. It may be in a different order or whatever, and I don't tell them what to do. I just throw out the things on the list, the Kevin Hart list, and at some point they go, oh yeah, that would work. So try that. You don't have to have it memorized. I'm not going to say, what are the 8 steps to success in simplifying? But if you don't have them all in your head, you're going to get stuck on problems like this, or maybe factoring, problems like this. All right? And you're going to see a lot more of this, but anyway, that's the simplifying stuff. Was there anything else on your that we did yesterday that gave you issues? Are we okay? Okay? All right. All right, so let's take a look at today. Today we're going to be looking at the alpha plus beta identities. So it would be a good idea if you just pulled out that identity sheet. And some people call them the alpha plus beta or alpha minus beta identity. Some people call them the sum or addition identities. But they're basically when you're taking a trig function of the sum or the difference of 2 angles. So for instance, if I'm taking the cosine of something like alpha minus beta, sadly, this is not cosine times alpha minus beta. I can't distribute it in because it's not a number, it's a function. And I don't know anything about cosine of alpha, maybe, and I don't know anything about cosine of beta, maybe, or maybe I do. But this is not asking me to find these two. it's asking me to subtract the two angles and then take the cosine. But a lot of times, when I subtract the two angles and take the cosine, I end up with something that I don't recognize from the unit circle. Like, I don't recognize what 15 degrees is. There's no special triangle with a 15-degree angle, is there? So what this identity allows me to do, it says, well, what if there were two angles that were on the unit circle? Like 45 and 30, that you do know the trig functions of, right? What if I replaced that with some sum or difference of two angles that are on the unit circle? Like, for instance, what if I replaced 15 with 45 minus 30? Is 45 minus 30 15 degrees? So if it is, I could take the cosine of that the same way I could take the cosine of that, because they're the same thing. Now, I don't know anything about this angle, but I know plenty about 45 and 30. So this allows me to go find the alpha minus beta identity for cosine. And again, it's not cosine 45 minus cosine 30. It is not. What is it if you're looking at your sheet? It is cosine of the first angle times cosine of the second angle. And then if that's a minus right here, you put a plus right here. And then you take sine of the first angle times the sine of the second angle. And there's a proof to that that's very clever. I think I did it for you guys last year. You actually drawing things on a unit circle and labeling alpha and labeling beta and doing some clever mathematics, and all of a sudden you end up with this formula. But now look, I'm basically changing this to this. I'm using my identity, and now I can figure out what cosine of 15 is based on angles and trig functions that I already know. So, what is cosine of 45 from your unit circle? Great. What is cosine of 30? Great. What is sine of 45? And then finally sine of 30. So all you end up with is root 6 over 4 plus root 2 over 4, which is root 6 plus root 2 over 4. And I can't add root 6 and root 2. If you remember from Algebra 2, it's like adding x's and y's. Unless I have the exact same radical, I can't do it. Y'all with me? Now, if that angle right there had been 14 degrees, well, I'm out of luck. I'm done. Because there are no angles on the unit circle that will add or subtract to give me 14. Now, there might be some other way that we won't learn in this course, but there are only certain angles that we can do. Okay? Now, if you see something like this, you could have, on this particular problem, subtracted these two, couldn't you? I mean, it's subtraction, right? You could find a common denominator, and you would get 4 pi over 6 minus pi over 6 is 3 pi over 6, right? You found a common denominator? And you know that 3 pi over 6 is pi over 2? So that happens to be the same thing as cosine of pi over 2, which you guys all know is what? 0. Now, I'm doing this for a reason. I want to point out to you why, if you just distributed the cosine, this is bad. Check it out. I already know that this should give me 0. But look, if I do that, I get cosine of 2 pi over 3, which is negative a half. I get cosine of 2, negative a half. I get cosine of pi over 6, which is positive square root of 3 over 2. That is not equal to 0, is it? That's why this method, distributing it doesn't work. Or one of the reasons why it doesn't work. But look what happens if I use the identity. Cosine of the first angle. Let's make this happy now. Cosine of the first angle. Sine of the second angle. Change from negative to positive. Oh, sorry. Cosine, cosine. Not cosine. Cosine, cosine. Change the SIGN. And then sine. Sine. Now check it out. Cosine at 2 pi over 3. Negative a half. Cosine at pi over 6. Square root of 3 over 2. Sine at 2 pi over 3. Square root of 3 over 2. Sine at pi over 6, 1/2. What is that plus that? So this identity is going to work for you. So the key is, if you ever have two angles, especially if you don't know, if you know those two angles, you recognize them from the unit circle, you can rewrite this as that expression. It's not always going to be a good idea, guys, to add or subtract these. Shall I get it? Or did you come back?
No.
Oh, that's quick. Throwing darts at you. Can I get the flu shot every year? How's it work? You know, I had it one time, sick for 3 months. It might have been a coincidence. Sick for 3 months, got pneumonia. I could not get rid of it. At one point, I went into the doctor and I was like, dude, give me something. He'd already given me like a couple steroid packs and antibiotics. And he goes, you know what my nurses are doing out in the hallway? I was like, what? They're looking at my throat swab of you. It's like, they said it was the most remarkable thing they've ever seen. I'm like, dude, get me well. But we're kind of scared of him now. I did get the flu really, really bad in college. You know, like where you like go to bed and literally don't wake up for 36 hours. And then you wake up to go to the bathroom and then you sleep another. I was so fever, aches, everything. Fell asleep on a Friday afternoon night, woke up on a Sunday night, and I hardly even remember what happened. And I was well. I was coming out of it. I was really weak and hadn't eaten anything in 2 days. But it's like after that, I haven't had the flu. It's like I'm kind of immune to that. But I still crank up some pneumonia occasionally. It's just a little scary. Are y'all with me so far? If y'all missed that, go check the video out, although we're going to do some more of this. But the key thing is, remember, you don't distribute, all right? And also, if I didn't start with this, and I started you with 45 minus 30, don't go around going, oh, 45 minus 30, that's equal to 15, awesome. Cosine of 15 is not going to help you. You don't know how to do that. So the idea of these is rewriting it so that you rewrite that value. You remember like when we were doing log of 5, and you didn't know how to do log of 5, but you rewrote it as log of 10 over 2 because 10 over 2 is equal to 5, and that allowed you some freedoms, right? Same kind of thinking. You're rewriting it. You're rewriting 15 as 45 minus 30. And if you're wondering, well, could I use 60 minus 45? Yes. Could I use 135 minus 120? Yes. Can I use 16 minus 1? Yes, but you're not going to get very far because I don't recognize 16 minus 1. So pick values that you recognize and use those, because if I recognize them here, in the identity, I'll be able to simplify them. Are y'all with me? And then also, it's going to become a little bit more confusing when you get to double angles. Because double angles, people are like, oh, well, 15, I could just multiply it by 2 and make it a double angle identity. Yeah. No. Because I can't really walk around multiplying by 2. If I could, where would I be? At the bank, right? So people that do this go, why can't I? Because 30 is not 15, is it? Now, could I do this? 30 over 2? That is 15. And there are half-angle identities that you could use in this, and we'll get to those later, probably tomorrow or whatever. Are y'all seeing this? Yeah, definitely tomorrow. We're going to do half-angle and double-angle tomorrow in that video. So yeah, I could rewrite it certain ways, but right now we're doing the alpha minus beta. All right, so let's look down a little further. What about sine of 255? Do you recognize 255 from your unit circle? I don't. 225, yeah. 315, yeah. 255, no. Now, are there two angles on the unit circle that you could add or subtract to get me 255? 300 and a negative 45 would work, right? So 300 minus 45, that's fine. 210 and 45 would get you there. Now, don't go 240 and 15. True statement. But what are you going to do with 15? You're stuck again, right? So find two angles that work for you. Now, I heard 300 and 45. So yes, if I wrote that out, that is the same thing as 255. Now, what is my sine of alpha minus beta identity? Well, the sine one says sine of the first angle times cosine of the second And you'll notice I don't look at the negative part. The negative comes out in the formula. And on sines, if that's negative here, it's going to be negative there. And then you do cosine of the first angle, sine of the second. Not too bad? And now pull out my unit circle now. What's the sine? And if you don't know your unit circle, guys, you're going to get beaten up on these. The sine at 300 is what? Great. Negative root 3 over 2. What's the cosine at 45? Root 2 over 2. The cosine at 300. And by the way, if I'm going to be doing 300 for sine, you can probably just knock them out both at the same time, right? I'm going right a little, down a lot. And then on the sine and the cosine, those are the same values. So what do I end up with? Negative root 6 minus root 2 over what? All over a 2 times 2, which is a quantity of 4. And that's this problem over and over again. Now, I'm going to show you the alpha plus beta, alpha minus beta for tangent, only so that you'll hate it, because it's crap. And if you have to use it, you have to use it. But if you ever have an opportunity to use a half angle instead for tangent, you're going to like it. Now, we aren't doing half angles. We're going to talk about half angles tomorrow. But, like, for instance, right here, isn't 17 pi over 12? If I think about that 12 as a 2 times a 6, isn't that the same thing as 17 pi over 6 divided by a 2? Think about it. If 12 is 2 times 6, then isn't this 17 pi over 6 over 2? Because to divide by that 2, I would multiply by a half, and you'd have the 2 and the 6 on the bottom. If you can ever rewrite something as a half angle, like if I had tangent of 15, yes, I can do 45 minus 30. But you're going to see why you hate it in a second. But if I could rewrite it as 30 over 2 and do a half angle identity, super easy for tangent. And I'll talk about that tomorrow again. But here, I said, hey, let's use a, well, maybe I didn't say it, but I'm going to use a alpha minus beta. Now, it's really tough for me to figure out the alpha minus beta when I see a weird radian like that. I mean, this is pretty easy with degrees. Radians, not so much. But don't we know how to change a radian to a degree? What do we multiply by? 180 over pi, because you want the pi's to cancel. So if I cancel the pi's out, 12 goes into that 15 times? And then 17 times 15 is what? 85, 255? So now that I got it as a degree, it's the same angle as this, right? But what would you use? Let's do something different this time. What angles would you use to add or subtract to give me 255? 225 and 30 is what I heard. So I'm going to rewrite this as, here, let me give myself some room because you're going to see this is awful. Tangent of, you said 225 plus 30? Okay, now here's the alpha plus beta for tangent. It starts out looking like a distributive property. Tangent 225 plus tangent 30. And you're feeling, oh yeah, distributive property. Not distributive property. Then you're going to divide the whole thing by 1 minus the product of what you just wrote up there. So if you wrote tangent 225 and tangent 30, then write them again, but this time multiply them together. And you'll notice when it's a plus, you use plus on the top, then minus on the bottom. And if it's a minus, you use minus on the top, then plus on the bottom. Yeah?
Can you do, like, wait, never mind.
Say it.
I was going to ask if you could do the tangent 225 plus tangent 30 for all of the functions, but I realized you wrote something under it.
Yeah, don't forget that. Or you don't go like, oh, you got part of it right. You just X'd. Are y'all with me? Okay, now, watch the cleanup on this. It's just a mess. So what's tangent of 225? Tangent of 225 degrees? Positive 1. And hopefully you have those memorized, right? All the 45, 135, 225, 1, 1, negative 1, right? And then what's the tangent of 30? Those are the low-lying ones. Remember what they are if you memorized them? Root 3 over 3. And then on the bottom, which is not 1 minus, you have the same two things again. So 1 root 3 over 3. Now this is a mess. Not only do I have to rationalize the denominator, but I have a denominator in the denominator. Like I have fractions within fractions. Now I'm going to show you a technique. I've showed you this before. You're going to do it 1,000 times in this chapter. So do it. It makes your life a little easier. To get rid of a fraction inside of a fraction, find the denominator of each term. The common denominator of each term. So what is the common denominator of all 4 of those terms? 3. Multiply the top and the bottom by 3 and just distribute it in there. That gives you 3. And then when you multiply by the fraction, the 3 goes away and leaves you just a root 3. And then you do it on the bottom, 3 minus a root 3. And already it looks a little better. So when you see a fraction within a fraction, just do that. It'll help you out. And we're going to do that a zillion times in this unit and beyond. Now what would you have to do? Multiply by the conjugates. You have to rationalize the denominator. So 3 plus a root 3, 3 plus a root 3, and now I got to FOIL the crud out of this. So that gives me on the top, let's start the FOILing. 9 plus 3 root 3, plus 3 root 3, plus regular 3. Let's start the FOILing on the bottom. Although at the bottom, because they're conjugates, the OI goes away. So I'm just going to go first times first is 9. Last times last, negative root 9, which is minus 3. And then when I clean up the top part, I get 12 plus 6 root 3. When I clean up the bottom part, I get 6. And if I cancel a 6 out of everything, I get 2 plus root 3. And that took me 1 step to do this, 1 step to write the formula out, which that's going to be the same no matter what I do, whether I do half angle or this. And then 1, 2, 3, 4, 5 steps to get the answer. The other formula is going to probably be 3 steps, 2 steps sometimes. Sometimes less. It really cleans up with a half angle nicely. We'll learn about that tomorrow. All right, we got 10 minutes. All right, let's check out number 5. Little ways you can be asked questions with this. Now, I want you to tell me, what am I really giving to you in these directions? In your own words, what am I giving to you when I tell you sine of x is 3 over 5 and x is between 0 and 90? I'm essentially giving you information about a triangle. I'm telling you, hey, there's some angle, because remember you always sine angles. There's some angle between here and here that has an opposite and adjacent of 3/5. Well, draw that sucker. And if I draw it, I can figure out the third side with Pythagorean identity, and then I can answer any questions I need to about it. So here we go. Oh, and what am I giving you about this thing? What am I giving you here? Another triangle. So I'm going to draw both of those over here. First, I'm going to draw my information about x. Now it's between 0 and 90, so it's somewhere in this quadrant. So I'm going to say, all right, here's my angle. There's x. And I know that the opposite and opposite and hypotenuse are 3/5. So here we go. The opposite, 3, hypotenuse 5, and that means the adjacent must have been 4. So that's angle x. Now I'm going to figure out about y. Y, it says, is in between 90 and 180. So I know angle y is over here, and technically that's the y right here. But a lot of times I think about it as on the inside. Okay, and what do I know about y? The adjacent over hypotenuse is negative 1/4. So the adjacent must have been what? Negative 1, hypotenuse 4, and with a little Pythagorean theorem, I can get root 15. And be careful when you put the other side in there. If you're going right or up, it's positive. If you're going left or down, it's negative. And make sure you put that sign in there. Biggest mistake, guess what it is on these kind of problems? The biggest mistake I see is people ignore this, and they just always draw a first quadrant angle or just draw a triangle. So all the sides end up being positive, and they don't acknowledge what could be happening to that other side. You got to put it in the right quadrant so you see what happens to that other side, because sometimes it'll be a negative. And if you don't see that, then you end up with positive values in your answer instead of the negative values that needed to be there. So now that I have this, tell me this. Do you know anything about the triangle do you know anything about the triangle whose angle is x minus y? You know anything about that triangle? You don't. Well, then let's get rid of this. How can I replace tangent of x minus y? How can I get rid of that so that it only has angle x and angle y in it as opposed to angle x minus y in it? Well, you pull out your what? Your alpha minus beta identity, or your x minus y identity. And what is that identity for tangent? Remember, it starts out like the distributive property. But on the bottom, you end up doing what? One, change that to a plus, and then just multiply those two together. And then all I got to do now is go to my pictures. Because I don't know the angle, but I know the picture of the angle. So what is the tangent of angle x? Anybody? 3/4? Now every year I have somebody who writes this. Tangent of 3/4. Tangent of root 15 over negative 1. They come in here and they do this. What did I do wrongly here? Is it the angle that's 3/4? No, it's the whole thing that's 3/4, right? So it's not that, it's just 3/4. And it's just root 15 over negative 1. And then if I put them there, I can also put them down here. And I know I don't like negatives on the bottom, I'm just doing that. And then to clean this up, like if I want to clean it up a little bit, I guess I could do this. I would not normally do this. But what do you have here that's annoying? You got 4s in the denominators. So even before I did this, what could I have done right here to clean this up? Multiply the top and the bottom by a 4. It would have looked a whole lot better if I had done that. So let's distribute it in. 4 times that leaves me a 3. Now those two negatives are going to become positive. 4 times that leaves me a 4 root 15, which is, granted, a little ugly. 4 times 1 gives me a 4. And then 4 times this fraction combination does still cancel the 4s and leaves me a negative 3 root 15. And at least at this point, what can I now do? Hello? What would I do at this point? Rationalize. So at this point, I'm going to multiply by the conjugate. I'm not going to do this. I'm just going to put dot, 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 because I think you know what to do at this point. So just continue to clean it all up. And you're going to see these kind of problems with alpha plus beta, alpha minus beta, for sine, cosine, tangent, whatever. By the way, you'll notice I didn't give you identities for cotangent, secant, and cosecant. So what could you do for a cotangent identity if you don't have any that I'm making you memorize? Yeah, instead of writing that one down, just flip it. So if that was a cotangent, I just put that on the top and that on the bottom. What could you do for a cosecant alpha minus beta? 1 over the big sine identity. Or just do the sine identity and then flip it at the end. Now you might have to rationalize it, do an extra step or whatever, but anyway. All right, look on the back side. A couple other things, different ways of seeing stuff. And this is where if you don't know your identities, the red flag's not going to go up, you're not going to recognize stuff, and you're going to be stumped. Now look at number 6. Do you recognize that identity? And again, you very well may not recognize anything because you haven't studied them. This is why you have to know them. Do you recognize that? Sine blah, cosine blah, minus cosine blah, sine blah. That's the sine of what? Sine of the alpha, same sign, beta identity. And what is the alpha in this case? 230, and the beta is the 30. Now you may look up here and go, well, why didn't you just plug in square root of 3 over 2 for that and 1/2 for that? Well, I could have, but it's going to be kind of unsimplified, still pretty ugly. And I think maybe this will clean up nicer. And sure enough, I can get it to 200 degrees. And to me, that looks better than sine 230 times root 3 over 2 minus cosine of 230 times 1/2. That was just ugly if I did that. So even though I could have done those two values like this is much simpler. Now, do you see any two unit circle angles that add or subtract to give me 200? I don't either. So if you don't, you're done. But if that had ended up being, I don't know, 255 or something, or 15 degrees, or some angle that you recognize, 75, that could be rewritten as two other angles added or subtracted, then you can go further. But in this case, I'm good. Can't go any further. What about this? I don't know how to do any of these angles with trig functions because they're not special. But do you recognize that identity? That is a what? That is a tangent of alpha minus beta. So that ends up being tangent of 90. Oh, and tangent of 90, I totally recognize that is undefined. What about number 8? Recognize it? Yeah, that's cosine, cosine minus sine, sine. That is a cosine of alpha what? Change the sine beta. So that's a cosine 15. Now, before I stop on that, like I did on 200, are there any angles that could add or subtract to give me 15? There are. So I'm going to change that to cosine of maybe 45 minus 30. And now I can use a different alpha minus beta to solve it. Cosine 45, cosine 30, plus sine 45, sine 30. And root 2 over 2, root 3 over 2, root 2 over 2, 1/2, root 6 plus root 2 over 4. And remember, you can't add a root 6 over root 2. Got 2 minutes. I'm going to let you play around with number 10, but I'm going to show you number 9. I'm going to get you started on it. This was actually one of the ones that was on your last test that I omitted. Check this out. Now you got to think for a second. At first glance, you're like, what the heck? This is awful. What is this? Remember how you sine an angle? What do you inverse tangent? A ratio or a value. And what do you end up with when you do an inverse tangent of a ratio? An angle. So this is really an angle. What happens when you inverse cosine a value? You get another angle. So what do I really have here? I have a sine of alpha minus beta. Are y'all seeing that? Now check this out. If that really is an angle, and that's really an angle, then how do I do sine of an angle minus an angle? Sine of alpha, cosine of beta, minus cosine of alpha, sine of beta. Except, what's my alpha? Arc tan of 2x. Arc tan or inverse tan of 2x. What's my beta? Arc cosine of beta. And guys, real quickly before you walk out, do you recognize how to do each of these? You should, because we did them on our last test. The ones where you draw the triangle and you figure out what it is. Yeah, you're going to have to do it a few times, but you can actually do these now. Y'all have a good one.